class, this video is the second in our series on fluvial erosion, and this is going to focus on the work water does when it's channelized in a defined area. And so once water is channeled, the erosion is going to be greatly enhanced. It's going to be concentrated in this area. Add to that any debris that the water is carrying along, you're going to see the erosion increase. So what we're going to talk about, like we will with all types of erosion, is how does this agent of erosion pick up sediment? How does it remove it? How does it transport it? And how does it deposit it? And we'll do this again when we talk about wind and when we talk about waves. So the first part is, how does water flowing in a defined channel erode the stream? So on this screen you see a couple of images. In the top hand corner, one way that streams erode their stream bed is through abrasion. So abrasion, if you could look into this little pothole, you would see a rock. And so when, like I said, water is carrying debris, the debris acts as a tool. So in the case of this, there are rocks in these potholes, and when water flows over this area, it swirls the water in the pothole around, moving around the rock, abrading the rock and abrading the stream bed. So these potholes will get larger and larger. Another way stream flow works to erode the stream bed is through chemical weathering. It's corrosive. So if you look on this image, you see the water back here. Do you notice how the rocks here look kind of smooth? And you can just imagine that maybe at some point water was flowing through here, maybe even over here. That smooth kind of surface is evidence of chemical weathering. Hydrolysis, we talked about that with the weathering, how hydrogen in the water interacts with certain materials in the rock and it turns them to clay, and then that clay is softer and more easily removed. If you ever drive up 395, right before you get to the cinder cone that we talked about, there is a sign that says Fossil Falls, and basically what it is it was ancient lava flow. It's basalt, and then they had water that would flow over the area, creating these waterfalls. The fossil is the waterfall because there's no water there now, and you can still see evidence so of the water that used to flow over this basalt. So it's pretty cool if you get a chance to go see it. Okay, the third way that streams erode their stream bed is through hydraulic action. That's just running water, picking up debris, picking up dirt, picking up sediment, and moving it. If we look at this image, well, let me get rid of that. Let's see. Here you can see that the stream has been eroding its stream bed. You see the water going over this nick point, but look at, here is the edge of the nick point over here and here, but right in this section it's back a little farther. That's because the water has been eroding the rock. When it tumbles down and it hits this area below it, it creates like a plunge pool. Maybe you've jumped off a waterfall and the water at the base of the waterfall can be deeper. Of course, you should never jump off a waterfall without knowing how deep that plunge pool is. So that's showing you evidence of erosion. Here's another example. Last summer, maybe it was the summer before, I went to Zion National Park and I hiked the Narrows. If you're ever looking for a place to go, put this on your list. It was great. I've always wanted to hike the Narrows, and you can only go at certain times of the year when the water level is lower. You can see my son in the picture right there. You can tell that where he's walking, the water obviously is not there. You can see that. But where do you think at times the water level could be? Hopefully you noticed over here this kind of concave shape. Yeah, this is where the water erodes this cliff. Now what will happen is, if the water continues to erode this cliff, this over part of the rock is going to give into gravity and the actual canyon will get wider. Now, the reason you have to go at certain times of the year is not only when the water level is low enough, because at points you're actually hiking in the water. And on the day we were hiking, it was up to my like chest, and I'm 5'2", so you can imagine how tall it was on that day in places. You also have to be careful of flash flooding. What that is if it rains somewhere upstream, all that water is going to be channeled down this river. Well, you can see here how steep these cliffs are. If there was a flash flood, you couldn't get out. And so they tell you when you're kind of checking in at the ranger station, they tell you what the likelihood of rain is anywhere in that area so that you can decide what the threat level is for flash flooding. Now here's another example. This is up in Jasper National Park. My middle dog's name is Jasper after the national park in Canada. You can see the water flowing over this waterfall. Do you think that the water level, the amount of water, is always this amount? Maybe you said yes, maybe you said no, maybe you're like, I have no idea. Well, look at the side of this rock. That tells you this kind of curved surface that at points this water is much greater, and that is what has eroded this stream bed. Here's another picture back to the Narrows. You can see now that we're walking in the water and the water goes from wall to wall. Some parts it's literally very narrow. Here's some evidence of abrasion. Remember, this water is carrying sediment. It's carrying rock. Some are large rocks, some are small rocks, some are gravel, some are sand. And what happens is it is when the water level is high enough, swirls these tools, these rocks, around in this area, abrading the sides of the cliff. I just love looking at pictures of water, and especially like I mentioned before that we don't necessarily have a lot of running water like this. At least I don't think it's so scenic. But anyways, this is in upstate New York. This is Watkins Glen Gorge, and basically it's part of the Finger Lakes. And the Finger Lakes were created by rivers running to the north, and then during the Pleistocene glaciers they came and carved out these river valleys, if you will. When the glaciers retreated, the debris called moraines were left behind. They kind of dammed up these river valleys and created these lakes. Well, another thing that happened is it sometimes creates a hanging valley, and I know we're not going to be talking about glaciers right now, but basically a hanging valley is, you imagine this huge glacier and some water is running into it. Well, when that glacier retreats, the difference in elevation from where that stream was to where the bottom of the glacier was can be several hundred feet. And that's what happened here. And so what it happens is that the gradient of the water, the gradient of the slope is steeper, so the velocity picks up. When velocity picks up, what happens? More erosion or deposition? More erosion, exactly. And that's what we see here. And this whole area is made up of different types of rock. So some of it is sandstone, some of it's limestone, some of it's really soft shells. And so that's why we see a series of nick points where the harder rock makes the ledge, the softer rock underneath it is eroded. So if you ever get a chance to go to upstate New York, check that out as well. Okay, so let's talk about stream transportation. So running water's picking up this sediment, right? It's got to take it somewhere. That's where the transportation part of it comes in. So when we talk about stream transportation, we talk about the stream load. That is the amount of sediment that's carried by this running water. And when we look at stream load, we can categorize it based on kind of the material and the size. So in this diagram over here, you can see how stream load can be divided into three categories, and I'm just going to use the pen to note which ones they are. So the first one is in a solution. That means that the running water has dissolved some minerals. Think back to like running water and sodium. Sodium would be dissolved. It would be carried in a solution. That's one aspect of stream load. The second aspect, so we'll say one here. The second aspect of stream load is all those really fine particles, that's a 2, sorry about that are carried in suspension. Think about like silt or clay that's carried never touching the bottom of the stream. So we have the suspended load. And then the third aspect of stream load is the bed load. These are all the larger particles that are pushed along the bottom of the stream. And how is bed load carried? One is through saltation. So larger rocks can skip along the bottom, bouncing along. And 2 is traction. Again, both of these are part of the bed load, and if they're not skipping along the bottom, then they're being pushed and rolled along the bottom. Now you can tell what type of stream load is being carried by looking at the stream. So we could tell, for example, well, you tell me, in this picture here, do you think that this stream, when it's flowing, I know it's a dry stream bed right now, do you think it carries most of its stream load in a solution as dissolved material, suspended, or as bed load? Hopefully you said bed load, and if I ask why, hopefully you said, well, I see all these larger rocks and pebbles. And I know that the larger particles are carried as bed load, and they are pushed along the bottom through traction or bouncing along through saltation. What about up here? This is the muddy Mississippi. It's called the muddy Mississippi because most of the Mississippi River's stream load is carried in suspension, and that's what gives it its muddy look. You could talk about the Yellow River in China, also has a lot of suspended sediment. Now, another aspect to stream transportation is the competence and the capacity. Stream competence tells you the largest particle size that can be carried. So if you think about a stream at its beginning, at its headwaters, in the mountains, in a steep slope, gravity is going to help that water move faster, and it's going to be able to carry larger particles. That's going to be very different than, let's say, the Mississippi River by the time it gets to its mouth, where it's carrying things that are more in suspended because a lot of the stuff has been broken down. Stream capacity tells you how much sediment can be carried. So I want you to think about a flood. How do you think a flood will affect stream competence and stream capacity? Will it go up? Will it go down? Well, during a flood type event, stream competence goes up. It can carry larger sizes sediment. And stream capacity goes up. It can carry more sediment. That's why floods can be very destructive, first of all, and a real effective way of shaping the land. So I told you when I was in New Orleans, I went to that Mississippi River Museum. So here's another picture I took from here. And in case you can't read it, this one says, okay, water. Rivers may run clear in places where natural obstacles like gravel, rocks, and trees capture sediment. This one says mud, too thick to drink and too thin to plow. Some waterways are brown from sediment suspended by the force of the current. And this is land. It says at the mouth of the river, and this is key here, the current slows, so the velocity goes down and sediments fall out. What that means is as velocity decreases, The fallout means deposition. That's a D. Increases. Okay? Okay, so last summer when I was making my journey across the country, I went back and I picked up a puppy. So this is Kelso, named after Kelso sand dunes. And the first place he wanted to go with me after I picked him up in Little Rock, Arkansas, was Memphis, Tennessee. So I had gone through there earlier on my way to Georgia, and when I flew back in to Atlanta, I drove to Little Rock to pick up Kelso, and then he and I drove back to Memphis and met my other son, who was headed from Annapolis, Maryland, down to Pensacola, Florida. So this was Kelso and I on the very first day that he became part of our family. And one of the things that we did was we went to this Mississippi River, which goes right through Memphis, and they have a park along the Mississippi River that has a scaled version of the Mississippi. How cool is that? So, what you see over here is they have actually created the Mississippi River from its headwaters to the Gulf. And as you walk along, you can see cities that are along the Mississippi. You can see how it meanders around. You get the idea of the depth of the river. You see the bridges crossing the river. It was fabulous. So, if you ever find yourself in Memphis, there are lots of things to do. Should definitely go to the Civil Rights Museum. You could go to Graceland if you want, but you should go definitely to see this Mississippi River model, which is right on the banks of the Mississippi River. And you can see close up that it's this brownish color because it's carrying its stream load in suspension. All right, so all good things must come to an end, and we have stream deposition. So remember, when the velocity decreases, the water can't carry as large of a particle, so it deposits it. So imagine the stream runs in to a large body of water, like this is the Mississippi River and this is the Gulf of Mexico. So it's a narrow defined channel. It gets into this big open water. What happens as the area goes up? Velocity goes down and deposition occurs. The name for stream deposited debris is called alluvium. And I want you to know that alluvium is well rounded. Why do you think it's rounded? Well, maybe you said, well, it's being chemically weathered all the way down. We know hydrolysis makes things kind of smooth and curved. Yes. What else is happening? Well, as it's being transported, some of the larger cobbles are being bounced along the river bank through saltation or traction, and that is a physical type of weathering, abrasion, right? Wearing it away. So they're rounded. So I want you to think about alluvium versus talus. What is talus? Talus is the debris that accumulates at the base of a cliff after a rock falls. That's very angular. That's very different looking than alluvium. The second thing I want you to know about alluvium is it is deposited in layers. You imagine as the water continues to flow, it deposits some, the next day more water, another layer. The third thing I want you to know about alluvium is it's well sorted by size. What happens when that water gets to that larger area and it slows down initially is it drops the larger particle. Let's just say gravel. Goes a little farther out, slows again. Now it has to drop the largest thing it's carrying now, which is sand. Goes out a little farther and it slows down even more. It has to drop out whatever is the largest thing it's carrying now, which is silt. And finally, way off the coast, it's going to deposit the smallest thing it's carrying, which is clay. Think back to our discussion about sedimentary rocks. They are formed in layers called strata. They have rocks called sandstone that are all sand-sized sediment, siltstone, all silt-sized sediment, shell, which is all clay-sized sediment, And so you can see why we get these sedimentary rocks is because of the work of streams and how it deposits things in this very well ordered, methodical way. Here's another picture. This one is up in the Cajon Pass. There is a dry riverbed here, but you can see that initially water deposited all of this sediment, and you can see that this layer here is thinner than this layer. And how do we know that this one? You can actually see that there are big rocks. Why do you think that we would have big rocks mixed in with little rocks, which make a conglomerate, by the way? Well, the answer lies in the fact that this water is not flowing all the time. Sometimes if you have a flash flood and there's a lot of water coming down, it would pick up mixed sized debris. Other times maybe it's a trickle of water and it has silt. Okay, so we'll see different types of sedimentary rock forming where water always runs and where it doesn't always run. So I hope this helps you to understand the work of water. Take care. Bye-bye.